Welcome to Learn with us. This is the 19th lecture of Basic Electronics.
First, we will have a quick review of your previous lecture. In your last lecture, you solved some examples of transistor circuits. What are the learning objectives of this lecture? In this lecture, you will study about collector characteristic curves. You will also understand DC load line. In this lecture, you will also study what is early effect. Now we will understand collector characteristic curves. We can generate a set of collector characteristic curves that show the relationship between collector current and collector to emitter voltage for specified values of base current. It means these curves show how the collector current varies with the collector to emitter voltage for specified values of base current. Now look at this figure. This figure is showing a family of IC versus VCE. It means collector current versus collector to emitter voltage for different values of base current. Now in this figure, this IB1 is less than IB2 and this IB3 is greater than this IB2 and so on. It means here we have IB1 which is less than IB2 and it is less than IB3 and so on. Okay, so this is your collector characteristic curve. Now we will understand how this collector characteristic curve is generated. Look at this circuit diagram. We know that this is an NPN transistor configuration. Okay, note that in this circuit diagram, both VBB and VCC are variable sources of voltage. Now if we assume that here this VBB is set to produce a certain value of IB, which is base current, and we know that the direction of base current is this. And if we also assume that here VCC is 0, okay, we know that here we have nodal voltage of collector and here we have nodal voltage of emitter. So if this VCC is 0, it means here this VC will be 0. And we know that this emitter is at ground here. It means here this VE will be 0 as well. Now here we know that the base emitter voltage is 0.7 volts in forward biased condition. Okay, it means here VB minus VE is equal to 0.7 volts. In this condition, VE is 0. It means here this VB is approximately at 0.7 volts. Now as you can see here, this VB is greater than VE. It means 0.7 volts is greater than 0 volts. Okay, so this junction is forward biased here and it is emitter based junction, and here this VB is greater than VC as well, that is 0.7 volts is greater than 0 volts. It means this collector base junction is also forward biased here. As you can see here, both the emitter base and collector base junctions are forward biased. It means the transistor here is in the saturation region of its operation. Okay, it means the transistor is in saturation mode here. Okay, and this saturation state is the state of a transistor in which the collector current has reached its maximum value and it is independent of base current. Okay, it means in saturation mode the collector current is independent of base current and it has reached its maximum value. Okay, in collector characteristic curve the variable of x-axis is collector to emitter voltage and the variable of y-axis is collector current. In our last slide, we assume that VCC is 0, due to which VC is 0 and VCE is also 0. Now as this VCC increases, VC increases, which in turn will increase collector to emitter voltage and it will increase collector current. Now here we have 0. So this IC increases with VCC but it continues to increase when this VCE remains less than 0.7 volts, because when this VCE is less than 0.7 volts, the collector base junction remains forward biased, and when this VCE is greater than 0.7 volts, this collector base junction becomes reverse biased. Okay. In our last slide, we said VB is approximately 0.7 volts, and we know that when VB is greater than VE, the emitter base junction is forward biased, and when this VC is greater than VB, the collector base junction is reverse biased. So when this VCE is greater than 0.7 volts, it means VC is greater than 0.7 volts, and it means now VC is greater than VB, making this collector base junction reverse biased. Now we know that this is the condition of active mode of operation. So when this VCE exceeds this 0.7 volts, then the transistor goes into the active mode of operation, and once this collector base junction is reverse biased, this collector current levels off and it remains essentially constant for a given value of base current. Okay. Now when this VCE continues to increase and it reaches a sufficiently high voltage, this reverse biased collector base junction goes into breakdown and the collector current increases rapidly. Okay. So now we can say that from this point to this point, this transistor is in saturation mode or saturation region, and from this point to this point, this transistor is in active mode or active region, and after this point, this transistor is in breakdown region. Okay, so this is how this collector characteristic curve is generated. We know that this is a family of collector characteristic curves showing relationship between collector current and collector to emitter voltage for different values of base current. Now if you look at this curve closely, as you can see, when this base current is 0, the transistor is in cutoff region. Although there is a very small amount of collector leakage current which is indicated by this line, it means there is some amount of collector leakage current even when this base current is 0 as illustrated in this graph. So what happens in cutoff region? As previously mentioned, when base current is 0, the transistor is in the cutoff region of its operation. We know that the equation of collector current is IC is equal to VCC minus VCE divided by RC, and if we rearrange this equation we get VCE is equal to VCC minus IC RC. We know that when IB is 0, there is a very small amount of collector leakage current, mainly due to thermally produced carrier, and this line here is showing this collector leakage current, and since this collector leakage current is extremely small, it will usually be neglected in circuit analysis. So we can say that this term is 0. It means now VCE is equal to VCC in cutoff region, and we know that in this cutoff region both the emitter base junction and the collector base junction, they are reverse biased. Now we know that this is a family of collector characteristic curves, and this region is saturation region. We know that the relationship between collector current and base current is given by this equation. IC is equal to beta IB, and according to this equation this IC is directly proportional to IB. So when this base current is increased, the collector current also increases. Now what about VCE? We know that from this equation IC is equal to VCC minus VCE divided by RC, and if we rearrange this equation, VCE is equal to VCC minus IC RC. This equation shows that this VCE is negatively related to this collector current. It means this VCE decreases as a result of increased collector current. Now when this VCE reaches its saturation value, which is VCE sat, the collector base junction becomes forward biased, and this collector current no longer increases even with a continued increase in base current. Now we say that this transistor is in saturation region, and at the point of this saturation this relationship is no longer valid, and in this case we have this equation IC saturation is equal to VCC minus VCE saturation divided by RC. Okay. Now look at this example. If you have a circuit like this, you know that this is an NPN transistor configuration where base current will flow in this direction, and this is the direction of collector current. We know that the relationship between base current and collector current is given by this equation. IC is equal to beta IB. We know that here beta is 100. Now if you want to sketch an ideal family of collector curves for this circuit, for base current ranging from 5 microamperes to 25 microamperes in 5 microamperes increments. So how you are going to start your analysis here? First, you will calculate values of collector current using this relationship. It means when this IB is 5 microamperes, this IC is 0.5 milliamperes. When this IB is 10 microamperes, this IC is 1.0 milliamperes. When it is 15 microamperes, it is 1.5 milliamperes. When it is 20 microamperes, this IC is 2.0 milliamperes. And when it is 25 microamperes, it is 2.5 milliamperes. Okay. Now we will draw the resulting collector curves here. We know that on x-axis we have collector to emitter voltage, and on y-axis we have collector current. As you can see, all these collector currents are in milliamperes. So here the unit will be milliamperes. Now when this IC is 0.5 milliamperes, we have this IB which is 5 microamperes. When this is 1 milliamperes, we have IB which is 10 microamperes. Okay, and when it is 1.5 milliamperes, we have IB which is 15 microamperes, and when it is 2 milliamperes, this IB is 20 microamperes, and when it is 2.5 milliamperes, we have this IB which is 25 microamperes. Okay, now here we have 0.7 volts. Okay, it means after 0.7 volts, this IC remains constant. Okay, so this is the family of collector curves when this base current is ranging from 5 microamperes to 25 microamperes. Okay. Now we will talk about DC load line. We know that on x-axis we have collector to emitter voltage, and on y-axis we have collector current. The relationship between this collector current and collector to emitter voltage at a specified value of base current is like this. We also know that this VCE is equal to VCC minus ICRC, and if we rearrange this equation, we get ICRC is equal to VCC minus VCE. Here this IC is equal to VCC divided by RC minus VCE divided by RC, and if we rearrange this, we get IC is equal to minus VCE divided by RC plus VCC divided by RC. We call this equation A. Okay. We know that the formula of slope is y is equal to mx plus c. Now if we compare this formula with this equation, we get y is equal to IC, because we know that the variable of y-axis is IC, and x is equal to VCE, because we know that the variable of x-axis is VCE. It means here this m is minus 1 upon RC, which is slope. This negative sign indicates that the direction of slope will be downward from left to right, like this, where this point is operating point Q. So this is slope or load line, which is minus 1 upon RC. Okay. Now at x-axis, this y coordinate will be 0. It means IC is 0. So if we put this value of IC in equation A, we get VCE divided by RC is equal to VCC divided by RC. This RC will cancel this RC. It means here VCE is equal to VCC. It means at this x-axis, here we have VCC. Now what about this y-axis? At y-axis, we know that this coordinate of x-axis is 0. It means here this VCE is 0. Now if we put this value in this equation A, we get IC is equal to VCC divided by RC. It means at this point we have VCC divided by RC. Okay. Now if we draw a line from this point Q on x-axis, we get VCE, and if we draw a line on y-axis, we get the value of IC. So these values of IC and VCE are coordinates of this operating point Q. Okay. If we draw DC load line on a family of collector characteristic curves, it looks like this. As you can see, the top of the load line is at saturation region, where collector current is equal to saturated collector current, as you can see here, and here the collector to emitter voltage is equal to saturated collector to emitter voltage, as you can see here. Now the bottom of this load line is at ideal cutoff region, where this collector current is 0 and collector to emitter voltage is equal to VCC. So this is the condition of saturation region, and this is the condition of cutoff region. Now in between this cutoff region and saturation region along the load line, there is the active region of the transistor's operation. It means from this point to this point, the transistor is in active mode. Now look at this example. If you have a circuit like this and you have to determine whether this transistor is in saturation region or not, so what would you do? First, we assume that here this saturated value of collector to emitter voltage is 0.2 volts. Now first we will find saturated collector current. We know that the equation of the saturated collector current is VCC minus VCE set divided by RC. Here we know that this VCC is 10 volts, this VCE set is 0.2 volts, and this RC is 1 kilo ohms. Now after solving this, you will get 9.8 milliamperes. Okay. Now we will find base current IB. We know that the equation of base current is IB is equal to VBB minus VBE divided by RB. Here this VBB is 3 volts, and in forward biased condition we know that the value of this VBE is 0.7 volts, and here this RB is 10 kilo ohms. So after solving this, you will get 0.23 milliamperes. Now we know that the relationship between collector current and base current is given by this equation. IC is equal to beta IB. Here we know that this beta is 50 and this IB is 0.23 milliamperes. After solving this, you will get IC is equal to 11.5 milliamperes. Okay, this shows that with this value of beta, this base current is capable of producing this amount of collector current, and as you can see, this collector current is greater than this saturated value of collector current. It means here this transistor is in saturation region, because this is the saturated value of collector current, and we know that if we further increase base current, the collector current remains at its saturation value. So in this case, the collector current will remain at this value of 9.8 milliamperes, and this value of collector current is never reached. So this is your answer. Now we will understand graphical representation of transistor characteristics. We know that the relationship between collector current and base to emitter voltage is given by this equation. IC is equal to IS e raised to the power VBE divided by NVT. As you can see, this is the exponential relationship between collector current and base to emitter voltage. So how you are going to draw this relationship? On x-axis there will be voltage, which is base to emitter voltage here, and on y-axis we have current, which is collector current here. Okay, so this exponential relationship is drawn like this. Okay, and at this point we have 0.7 volts. Okay, so this is the exponential relationship between collector current and base to emitter voltage for NPN transistor. Now what about base current? We know that the relationship between base current and collector current is given by this equation. IC is equal to beta IB. So if we put this value of IC in this equation, we get beta IB is equal to IS e raised to the power VBE divided by NVT, and it means base current is equal to IS divided by beta e raised to the power VBE divided by NVT. Now what about emitter current IE? We know that the relationship between collector current and emitter current is given by this equation. IC is equal to alpha IE. Now if we substitute this value of IC in this equation, we get alpha IE is equal to IS e raised to the power VBE divided by NVT. It means emitter current is equal to IS divided by alpha e raised to the power VBE divided by NVT. Okay, it shows that the relationship between base current and base to emitter voltage and emitter current and base to emitter voltage, they are also exponential but with different scale currents like Is divided by beta in this case and Is divided by alpha in this case. Okay. Now, what is the effect of temperature on collector current and base to emitter voltage characteristic curve? We know that the relationship between collector current and base to emitter voltage is exponential, which is drawn like this, where on x-axis we have base to emitter voltage and on y-axis we have collector current. For suppose this relationship is at temperature T1. Now when this temperature is increased, this relationship looks like this. Now this temperature is T2. Now if this temperature is further increased, then this relationship looks like this. Now this temperature is T3. It means when this temperature is increased, the base to emitter voltage decreases. Now in case of silicon diodes, the voltage across the emitter base junction decreases by about 2 millivolts for each rise of 1 degree centigrade in temperature, provided the junction is operating at a constant current. So this is the effect of temperature on this characteristic curve. Now we will understand early effect in ideal bipolar junction transistors. The relationship between collector current and collector to emitter voltage is drawn like this. It means it is a perfectly horizontal straight line. Now for a family of collector characteristic curves, this relationship looks like this. Now, what about practical bipolar junction transistors? In practical bipolar junction transistors, these characteristic curves are not perfectly horizontal straight lines. They are like this. Okay. Now here we will draw the negative axis of this collector to emitter voltage here. Now in practical bipolar junction transistor, these characteristic curves are extrapolated and these extrapolated lines meet at a point on the negative collector to emitter voltage axis. It means if we extrapolate these lines like this, they will meet at a point here on negative VCE axis and we call this point VA. Now this voltage VA is a positive number which is a parameter for this practical bipolar junction transistor with typical values in the range of 10 volts to 100 volts, and it is called the early voltage, and this effect is called the early effect. Now, in case of ideal bipolar junction transistors, output resistance is finite and early voltage is 0. So in this case, the equation of collector current is Is e raised to the power VBE divided by NVT. Here this N is 1. So this equation becomes Is e raised to the power VBE divided by VT. Okay. Now in case of practical bipolar junction transistors, this output resistance is not finite and this early voltage is not 0. So in this case, the equation of collector current becomes Is e raised to the power VBE divided by VT, and here we have 1 plus VCE divided by VA, and now we call this equation A. Okay. Now from Ohm's law, we know that V is equal to IR. It means I is equal to V upon R, and R is equal to V upon I. Okay, and 1 upon R will be equal to I upon V. Okay, now in this case we know that R is equal to R naught, I is equal to IC, and V is equal to VCE. Okay, so this equation can be rewritten as 1 upon R naught is equal to IC divided by VCE. Now, if there is a change in this collector current with respect to this collector to emitter voltage, this equation looks like this. Now, in terms of partial differentiation, this equation is written like this. Now we know that this IC is equal to this term in case of practical bipolar junction transistors. So if we substitute this value here, our equation becomes ISE VBE divided by VT, and here we have 1 plus VCE divided by VA. Okay. Now we'll open this bracket. We'll get this equation ISE VBE divided by VT plus ISE VBE divided by VT VCE divided by VA. Okay. Now we will partial differentiate this whole term with respect to this VCE, and we know that in this term there is no term which is related to this VC. It means there is no VCE in this term, so this term becomes 0, and we have VCE here. So our answer of partial differentiation will be ISE VBE divided by VT multiplied by 1 upon VA. Okay, now we have this equation. We know that this value is equal to IC, as you can see here. So this equation becomes something like this. And if we rearrange this equation, we get output resistance is equal to VA divided by IC. It means output resistance is equal to early voltage divided by collector current. Now that's all for today. What are the key takeaways of this lecture? In this lecture, you studied about collector characteristic curves. You also understood DC load line. In this lecture, you also studied about effect of temperature on collector characteristic curves, and you also understood what is early effect.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.